Hello, Math 112 fans. Going to continue this series to get you ready for our final next week. This is part 4 where I'm going to talk about analyzing functions. To me, this is the biggest thing that I hope all my students and all my calculus classes take away from the value of derivatives, is that we can use the derivative to figure out a lot about a function and how it behaves, which is pretty valuable for really anyone, no matter what they're going to use it for. So what I'm going to do is give a brief review, and then I'm going to look at a collection of old final questions that relate to this. I do want to remind you I have a lot of review materials here. This is talking about Chapter 10 material, where we talked about this thing I call the Rosetta Stone of calculus, which is that if you're studying some function, doesn't matter what it is or where it came from, and you want to know information about its height, you work with the function. If you want to know information about its slope, you take the derivative. And if you want to know information about its concavity, you take its second derivative. And these are the connections we used over and over again. I handed out these review sheets. We talked about this. You can formally think about the process, but it's really 3 things, which I'll talk about here in a second. And I have several examples in that review. And then I have this, which is just like a quick summary of global, max, and min, and basically the 5 types of questions we ask. Honestly, I think of it as 3 questions. So I'm going to give that brief recap here in a second, and then we're going to pull up some old finals, and I'll keep that there so that we can study. Okay, so here I have a function on the left. This is actually from one of my review sheets, but it could be anything. So the first thing you need to remember is that if you're studying this function and you graph it, the graph tells you the height. I notice sometimes that students don't know that fact, even in my calculus series. So if you plug in the number 2 to this thing, it'll tell you how high it is if you were to graph it. In this case, that'd be 8 minus 24, so it actually is below the axis. It's down here. That's height. The derivative tells you the slope, 3x squared minus 12. And what we mean by slope is slope of the tangent line. There are secant lines and other things we talk about in Math 111 and when we were doing this, but this is the slope of the tangent line. And then the second derivative tells us this thing we're calling concavity. And really the only thing we use that for is if the concavity is positive or negative, then we know the function's increasing or decreasing. Okay, so let's talk about what we can then use those for. So some of what we can do is just that alone, which is really helpful. Like when you're at the top of a hill, what can you say? You can say the slope is 0. So we want to find the slope. When you're going, when you switch from speeding up to slowing down, there's this certain special moment where you changed from slowing down to speeding up. That's the inflection point. That's the second derivative. Okay, so those are questions we naturally ask. Okay, so now let's talk about the formal things that we've been doing. If a question on your test asks you for increasing, decreasing, horizontal tangent, max, min, those all have to do with slope. So any question that says max, min, and there are lots of synonyms in the English language. Largest, smallest, increasing, decreasing. That's it, but we could say it if you any mention of that, you're going to find the first derivative and set it equal to 0. I think of this as the first derivative analysis. This is our main weapon in analyzing functions, and it's one of the 3 main types of questions. So you take the first derivative, y prime, and you find when it's equal to 0. The reason we find when it's equal to 0 is because the places when the slope is 0 are valuable to us. They're the high points and low points. They also tell you when you stop increasing or decreasing. So that's step 1. I say step 0 is understand what the question's asking and identify what it's talking about. So if we're talking about this being our original function, whatever it is we're studying, and then you're asked about the max, min, increasing, decreasing, we take the derivative and set it equal to 0 and solve. So I'll illustrate this. X squared is 4, and that means x is plus or minus 2. Done. Okay, so then let's go. Step 2. Step 2 is just making conclusions from this. And if the question is asking about max, min, increasing, decreasing, you're trying to make conclusions. And so I have a particular way I've been suggesting you do this, which is to draw a number line, make a little mark at -2, make a little mark at 2, and then talk about what the derivative tells you, and then make conclusions about what that tells you about the function. And I like to organize it this way. So how do we do that? We look back up here at our derivative, and we ask ourselves, is it positive or negative in each one of these 3 regions, before -2, between -2 and 2. And I think something about that bothers people, but pick a number less than -2. I talked about how ideally you wouldn't even pick a number. You would just think about what happens when you plug in something here. So you can pick a number. You could pick -3 or -4 or -5 or -6 or -7, any of those, and see what you get. And I was going to show my calculator, but this is when you would do, if you wanted to do a little bit of calculator work. So you do have to type it in correctly. It's not bad to type in a few. Let's do -3. So I'm going to type in -3. You really don't need a calculator for this, but I've seen so many students doing this, I want to write it. It was +15. You don't even need to write down the value. You just need to say it's positive. This will be positive. So I plugged in a -3 and I got a positive number. Most of the time, you don't even need to plug in your calculator. You can tell. Like I could already tell that was positive because 3, so it's going to be 27. I knew. I didn't need a calculator, but you could do it if you wanted step by step. That tells me the original function is increasing. Let's pull up our Rosetta Stone of calculus again. This is what we're using every time we do an application, and we just used it. Positive slope was positive, so the original function's uphill. Now we keep going. If we plug in a 0 to the derivative, what does it tell us about the slope? And really, some people are like, I don't know where to plug it in. Well, right now we're trying to figure out if the slope is positive or negative. So the thing you're going to plug into is slope. Okay, so we plug in a 0. It's negative. That means the original function is downhill. And lastly, we can plug in a 3 or a 4 or a 5, and we should see already that it's going to be positive because we're going to get the same thing as we got there. So students don't like that it takes a few steps, but really it's not very long. And the moment you do that, you've answered every possible question about local max, local min, increasing, decreasing. If the question says when is the function decreasing, you would say from -2 to 2. If the question said when is the function increasing, you would see before -2 and after 2. If the question asked for whether it was a local max or min, you would call this a local max. You would call that a local min. That's why I like drawing those arrows. So the main conclusion from this, if I zoom out a little bit, I hope this is okay. I know it's probably taking too long and everyone's turned it off, but I really want to get these ideas for those of you that haven't figured this out yet. So we could say at x equals -2, there's a local max, and at x equals 2, there's a local min. And if you're trying to understand what the graph looks like, that's probably the first thing you do, what we just did there. So let's put a little box around it. So anything that's about increasing, decreasing, local max, local min, that's what we do. Okay, what's another type of question? Another type of question is a global max and min. So I'll do this right next to this because it's so close to this. So a question that's asking about global max and min or absolute max and min, we've had a couple ways of saying it, is asking about what the biggest overall is in an interval. So a question like this would say, find the global max and min for this function, x cubed minus 12x, and then they'd give you an interval from, let's say, x equals 0 to x equals 3. And I didn't pick these numbers ahead of time. How can you tell it's a global max question? It will say something about the largest or smallest on an interval. And the process for this is initially the same. We just do one thing different at the end. And we've already talked about this, and I did several in class. But step 1, take the derivative, set it equal to 0, and solve. Now, since we already did that, I'm just going to write it here. Step 2, You could draw the number line, but it's not necessary because the question is not asking about whether it's a local max and min. Global max and min, the number one thing is you plug into the original function at the end, the original y. And in this case, there are three things to plug in. There's the endpoints, x equals 0, so you plug in the endpoints, and any critical numbers between the endpoints. In the interval. Okay, so in this case, the endpoints are 0 and 3. And we talked about this visually, why the maximum of a function either has to be at the endpoints or at a critical number. And there's only one critical number between 0 and 3, which is 2. And then we compute. So what are the things we compute? We need to know global max and min is talking about overall height. That's why we're plugging into the height at the end. So if we plug in 0 to the original function, we get 0 cubed minus 12 times 0, which is 0. If we plug in 2, we get 2 cubed minus 12 times 2, which is 8 minus 24. Again, I didn't prepare this, but I think that's minus 16. And then we plug in a 3, we get 3 cubed minus 12 times 3. And so we get 27 minus 36. 27 minus 36. I think it's negative 9. So again, I did not pick these numbers carefully, but then we would call this the max, the global max, and we would call this the min. That's how we do absolute or global max and min questions. And before I do the last one, that's really the main skills right there. Before I do the last one, I am going to pull up this example to show you a quick visual. So this all comes from this review, and this is, I said, the biggest skill is that you understand these principles. You can see I do several examples in that review. So what we just did was this. Let's just double check I didn't do anything silly. I took the derivative, set it equals 0. We got those two values. Increasing, decreasing, increasing, we did our analysis. We'll do the second derivative step in a second, but that's what the graph looks like. Increasing, decreasing, increasing. So it makes sense if I grab this. Sorry, I wasn't ready for this yet. I'm going to grab this real quick. There's our function. So when I asked about the max and min, from 0 to 3, we were only looking in this box. And the maximum of a function on a given box has to occur at a bump inside the box or at an endpoint. And we found out that this was at negative 9, this was at negative 16, and this was at 0. And we didn't need to see the picture. We knew it had to be one of those. So that's why 0 was the maximum, negative 16 was the minimum. I like global max. It makes sense to me. It makes logical sense. That's really it. I would say most of the 97% of the time that we're analyzing a function, that's all we're doing, is taking the first derivative, set it equal to 0, and then it's just a question of what we want to do with that information. Do we want to analyze it and figure out when it's increasing or decreasing, or do we just want to know the output? So to me, that's not too bad to sort that out. All right, one other type of question, which is really a specialized question, but I'm going to squeeze it in here and move things over a little bit. And then I'll look at old exams, and we'll just identify the type of question. Okay, last type of question here, which is what can we extract from the second derivative? So that would be a question about concavity or inflection. So if it says concavity or inflection, that's what we got. And so let's run through that process. Step 1. Once you know what function you're talking about, you find its second derivative. In this case, the second derivative is 6x. You set that equal to 0, you get x equals 0. Step 2. You do your analysis. So let's do our second derivative analysis. The only point we got is 0. So then right here we write second derivative, function. And we do the same thing we did before. If you plug in a number to the second derivative, is it positive or negative? Once again, we're using the translation table of calculus, the Rosetta Stone, as I like to jokingly call it. But now we're translating from the second derivative to the function. And we talked about why this is, but that's another discussion. Okay, so if I plug in a number less than 0, we should already see it's going to be 6 times a negative number, so it's going to be negative. If we plug in something bigger than 0, it's going to be 6 times a positive number, so it's positive. What that means is your function is part of a frown or part of a smile. That doesn't mean it's an entire frown or smile. It just means it's part of a smile or frown. So, and that means that this is called an inflection point. If it changes, we would say x equals 0 is an inflection point. And that's this point right in the middle where it switched from a frown to a smile. That gives you added confirmation about the other analysis we did, because it confirms that this is indeed a minimum because it's concave up. It confirms that this is indeed a maximum because it's concave down. So it's nice. The one added thing we get out of this is confirmation. Okay, so download that to your brain. I think I'll stop this video and then I'll go through the exams. So this will be part 4A of analyzing functions. And then we'll just play the game of looking at the exams.